For centuries, human beings looked toward the sky and imagined what it would feel like to fly. Birds made it look effortless, gliding across oceans and soaring above mountains without engines, without metal, without noise. For early civilizations, flight was mystery and mythology. Gravity appeared absolute. Everything that rose eventually returned to the ground. Yet curiosity never faded. Over time, imagination turned into experimentation, and experimentation turned into science. Today, powered flight is no longer a miracle. It is a precisely engineered system built on the laws of physics. To understand how airplanes actually fly, we can examine a real-world example, the Boeing 777. This wide-body, long-range aircraft is capable of carrying hundreds of passengers and heavy cargo across continents without stopping. When fully loaded, it weighs hundreds of thousands of kilograms. Despite this immense weight, it accelerates down a runway, lifts smoothly into the air, and cruises at altitudes where the air is thin and temperatures are far below freezing. The reason it can do this is not magic. It is balance, specifically, the balance of four fundamental forces: lift, weight, thrust, and drag. Weight is the force of gravity pulling the airplane downward. Lift is the upward force created by airflow over the wings. Thrust moves the aircraft forward, generated by its powerful turbofan engines. Drag is the resistance produced by air opposing the airplane's motion. These four forces are always present, and flight occurs only when they are properly balanced. When thrust exceeds drag, the airplane accelerates. When lift becomes greater than weight, it rises into the sky. The most critical component of flight is the wing. The Boeing 777's wings are not flat panels. They are shaped with a curved upper surface and a flatter lower surface, a design known as an airfoil. As the airplane moves forward, air flows over and under the wings. Because of their curved shape, air traveling across the top surface moves faster than the air underneath. According to aerodynamic principles, faster-moving air creates lower pressure. Slower-moving air creates higher pressure. This pressure difference produces lift, pushing the wing upward. At the same time, the wings push air downward. Newton's third law states that for every action, there is an equal and opposite reaction. By deflecting air downward, the wings generate an upward reaction force. Together, pressure difference and downward airflow create the lift necessary to overcome weight. However, lift depends on speed. Without forward motion, airflow is insufficient to generate the pressure difference required for takeoff. That is why thrust is essential. The Boeing 777 uses two large high-bypass turbofan engines mounted beneath its wings. These engines pull in massive amounts of air, compress it, mix it with fuel, ignite the mixture, and expel it backward at high velocity. This produces thrust, pushing the airplane forward and allowing air to move rapidly across the wings. During takeoff, the Boeing 777 accelerates along the runway as engine power increases. As speed builds, airflow strengthens over the wings, and lift increases. At a precisely calculated speed known as rotation speed, the pilot gently raises the nose of the aircraft. This increases the angle of attack, the angle between the wing and the airflow, generating even more lift. Within seconds, lift exceeds weight, and the airplane leaves the ground. After liftoff, the landing gear retracts to reduce drag. The aircraft begins climbing to cruising altitude, often around 35,000 feet. As altitude increases, air density decreases. Thinner air reduces drag, improving fuel efficiency, but it also requires careful speed management to maintain lift. The Boeing 777's flight control systems constantly adjust engine power and control surfaces to maintain optimal performance. Once at cruising altitude, the airplane enters a state of equilibrium. Lift balances weight. Thrust balances drag. The engines operate at steady power settings, and the aircraft moves smoothly through the upper atmosphere. Modern avionics and autopilot systems monitor altitude, speed, and heading, ensuring stability over long distances. Even small movements are carefully controlled by ailerons, elevators, and the rudder, allowing precise adjustments in roll, pitch, and yaw. Eventually, the aircraft must return to the ground. Descent begins with a gradual reduction in thrust. As the airplane slows, pilots deploy flaps along the trailing edges of the wings. Flaps increase both lift and drag, allowing the airplane to fly safely at lower speeds. The landing gear is extended, further increasing drag and stabilizing the aircraft for approach. On final approach, the Boeing 777 aligns precisely with the runway centerline. Speed, altitude, and descent angle are continuously adjusted to ensure a smooth landing. Just before touchdown, the pilot gently reduces power and slightly raises the nose to decrease descent rate. The main landing gear makes contact with the runway, and spoilers deploy on the wings to reduce lift. Reverse thrust is activated, redirecting engine airflow forward to help slow the aircraft. As the airplane decelerates and exits the runway, the four forces that once lifted it into the sky gradually return to a resting balance. The science of flight remains constant from takeoff to landing. Lift, weight, thrust, and drag never disappear, they simply shift in dominance at different stages of flight. The Boeing 777 does not defeat gravity. It works within the laws of physics, using aerodynamic design and controlled power to achieve stable flight. What once seemed impossible is now routine, repeated thousands of times each day around the world. And every time an aircraft rises into the sky, it stands as a reminder that human curiosity, guided by science, can transform dreams into reality.